Today, I'm going to present to you two 8-bit adder, which is created using the final state machine. This is the adder which adds 8-bit number A and 8-bit number B and displays it in this shift register. Okay. So first step, in order to create it, we have to create a Moore machine. Okay, so in the Moore machine, we are going to use, in order to create the Moore machine for this FSM, we're going to use two inputs. So those inputs are start and stop. And we are also going to use three outputs. So the outputs are init, add, and done. And this final state machine, this FSM, is going to have three states. So the first state, I'm going to call it init state. So this is the state which we are initializing the numbers. Then the first state is going to be add state. This is the state in which we are going to add the numbers. And then the last state is S2. And this is the state which is called done state. And this is the state which are going to use after we add those two numbers. So, as I mentioned before, this is going to be Moore machine. So, S0 we are going to have values of the output. So the output is init, add, and done. And as the first state is init state, initializing state, we are going to have init set to 1. Then we are not adding anything, so add is 0, and we are not done, so done is 0. This is our first state. Then the next state is state 1, in which we are going to add numbers. So init is going to be 0, add is going to be 1, and then done is going to be 0 because we are not done. And then the last state, S2, this is going to be init is 0, add is equal to 0, and then done 1 because we are done with everything. We have two numbers added. Okay. Now the connection between the states. So in the first state, the start button is going to trigger our machine. So if start is 1 and stop is 0, we are going to move to the next step. Before I go further, I'm going to mark the axis. So this is start, comma, stop, and then those are init. This is add. This is done. Okay. So if we have both of those inputs, start and stop 0, we are going to stay in the same state. If start is 0 and stop is 1, we are not going anywhere. So again, we are in the same state. And then if they are both 1, I'm not going to start the machine. I'm going to stop the machine because I think stop in this case is more important than start. Okay. So now after we are in this state, in the state 1, this is the state when we are adding everything. So of course, if start and stop is 0, we are going to stay in the state. Then if start is 1 and stop is 0, I think I'm going to continue with adding. And then if both are 1s, I'm also going to continue with addition. And then in this case, start is 0 and stop is 1. It means that we are done with everything. We're done with counting the numbers, with adding the numbers. So now we are in the done state. And the done state, we're going to move to the S0 state in the case with, let's say, start is 0, stop is 1, and let's say if both are 1. And in another other case, we are going to stay in the state. So if it's 0 and 0, we are going to stay in this one. And then in the case when start is 1 and stop is 0, we are also going to stay in this state. So this is my whole Moore machine. Now let's move on to the code. So if we go to the ISP level, we can go to FSM calls. Okay, and let's have them side by side. Okay, so the first step in the FSM is going to be initializing the ports. So as I said, we have stop and start as an input, but we also have a clock which is going to connect with almost every block, so it's going to be synchronous. And then we have resets in order to reset everything. And the output is the init, add, and done. Then I have initialized the states. So the states are 2-bit numbers. We have 3 states. State 0, which is init, state 1, which is add, and then state 2, which is done. After initializing the states, I have 3 processes. So the first process is the memory process, in which I'm going to reset everything. If the reset is high, then we are going to go to the state 0. But in the case if reset is 0, we have to check if there's a rising edge of the clock, and if there is a rising edge of the clock, we're going to move on to the next step or to the next state. And those 2 processes are the ones which describe the Moore machine. The first process is going to describe the transition between the states. So when we are in the state 0, as here, if start is 1 and stop is 0, we are going to move to the step 1. And then if we are and then in other cases, we are going to stay in this state. For the state 1, if the start is 0 and stop is 1, we are moving to the next state. And in another case, we are going to stay. We're going to move on to the next state. Yes, no, sorry, we're going to stay in this state. Then for other states, which is S2, if start is 1 and stop is 0, we are moving to the next state. And then if start is 1 and stop is 1, we are going to move to the next state. And in another case, we are going to stay in the state done. And this process is called data process because this is the process which describes the data which is inside the state. So when we are in the state 0, we know that add is 0, init is 1, done is 0. And then when we are in the state of addition, we are going to have add is 1, and the rest of them are 0. And the other case, which is the last state 2, we have add 0, init 0, and then done 1. And that is for the Moore machine. Now let's go ahead and see the code which connects all of those together. It's this one. So I'm going to put this one on this side and then this one on this side. Okay, so in order to connect all of those blocks, first I had to create a port for our new entity. So the new entity is the whole block of those smaller blocks. And it has the input reset, start, and clock. It has 2 8-bit numbers, A and B, which we are going to add, and then it has Y output, which is a 9-bit output, and this is the sum of those 2 numbers. There's also done output, which outputs 1 after we are done adding those numbers. In order to connect those blocks, I had to implement components and ports for those components. So the first component is FSM machine, and as I said before, it has those 4 inputs and 3 outputs: stop, clock, reset, and start. And init, add, done is the output. Then I copied and paste the ports from every component. So this is the counter. Counter has load, enable, and clock. As you can see here, it's load, enable, and counter, and clock, and clock. And then we have full adder, which is basically 3 ports, A, B, C, and then zoom and cout, which is carry. Flip flop, this is the deep flip flop, so it has the D input, clear, clock, and Q, and 2 registers. This one is used to display the output number, and this one is used to display input numbers, so A and B. I initialized a few signals in order to connect the blocks. So let's move on to the port maps of those. So in this part of this code, I connected a few blocks with the either signal or other block. So the first one is our final state machine. So I connected the stop signal with the stop input with the zero stop signal. So let's see. We can see that the final state machine has stop input, and I created here a signal which is called zero stop, because it connects output 0 from the counter to the stop input of the FSM. Okay, next one is the clock. I can clock the clock, reset to the reset, start to start, init to init signal, because this is the signal which travels through this lane, init lane. And then I have I have add to add signal. So the add signal is the signal which travels through the lane of the signal, add signal. So if we take a look at this one, this is the signal which connects add with the registers and also with the counter. Also with the counter and the shift register. Okay. Erase everything. Okay. So now we are going to see the counter. The counter is, of course, as I mentioned before, load is connected with the in signal and enable is connected with the up signal. The X is 8 because we are going to count up from 8 to 16, and so from 8 to 16, from 8 to 16, there's 8 steps, and then we are going to 0. So the total is 9 steps, and the reason for that is because we are going to add 2 8-bit numbers, but the result is a 9-bit number, so we have to have 9 steps. Okay. Okay. So then we have the registers. We have 2 U registers for 2 numbers, for A number and for B number. Of course, loud is connected with the in signal, shift right connected with the up signal, clock with the clock, X which is the input connected with the A, so the input of the register, and then listening some bit is connected with the listening some bit A signal. Same with the other one. Full adder is connected A to listening some bit of A, B with the listening some bit of the B, C with the output of the flip-flop, of the D flip-flop. Sum is with the input sum, and then carry is connected with the C out D signal, which is connected to the D flip-flop, as you can see here. Then I have the S register, which is of course clock to the clock, shift right to add signal, input to the sum input, and so on. Okay, so let's go ahead and actually see if it works. So this is the test bench. And in the test bench we can, oh sorry, it's here. It was already here. Okay, so this is the test bench, and as you can see, let me open this. Okay, so we have 2 numbers. We have 2C number in binary and 91 number in the binary, and it has 9 steps. In each step it adds the next numbers, next binary numbers, and in the end we have the full addition. So 2C plus 91 at 0 BD in the hexadecimal number. And that's it. That's the whole code for this 2 8-bit adder. Thank you for your attention.